Hello, everybody. It's good to see you. Good to see so many of you. Welcome to the British Interplanetary Society's West Midlands branch. I'm Bob Stanton. In a moment, I'll be introducing you to, believe it or not, my daughter, Amelia Stanton, who's giving today's talk on additive manufacturing. Patrick, stop laughing. I can see you there. But before we do, I'd like to run through a few things. So I'm just going to share my screen with you so you can see. Right, calls for new papers, articles and website material. So they're always asking us if we can find new sources of material. So if you have, please do get in touch. They'll be only too happy to talk to you. And moving on, membership while social distancing. We've got, I noticed that about just over half of you here today are non-members, and I notice a few of you are coming to quite a few of our events, and I think you're missing out. You should join. You should join because we've got hundreds of hours of videos which you can binge watch, like I did when I first joined, from various talks, symposia, conferences, and so on. Really exciting stuff. We've got Spaceflight magazine, I think it's probably the leading astronautics magazine to keep up to date. We've got the Journal of the British Interplanetary Society, a peer-reviewed journal. We've got Space Chronicle, which comes out quarterly. You get a monthly newsletter. And there's all sorts of things on the members-only section of the website. If you're not already a member and you're coming again and again to our meetings, join, because you're missing out. You're missing out. Go and join today, and you can. And let's have a look. Yes, and you can get there. It is bis-space.com/get involved. I'm going to stick that in the chat once Amelia starts talking as well. Now, today's speaker is Amelia Stanton. I think I mentioned earlier, she is my daughter, so it's a proud moment for me. And I'd like to say thanks to Mark, by the way, for letting me do the introduction. I begged him if I could to do it. So Amelia is a student at Heriot-Watt University studying mechanical engineering on the integrated master's course. And she's going to enter her final year now. And she completed her dissertation, the use of additive manufacturing for aerospace combustion chambers, earlier this year. And so a few other things she's been up to. Last year, she worked with the International Space Elevator Consortium, and she wrote a paper on engineering the Apex anchor. This year, she's working with the Institute Initiative for Interstellar Studies, I4IS, and she's just finished a course mainly with Rob Swinney, but also with, I'm going to drop a few names here. We've got Brian K. Kelly, the former director of the Johnson Space Center for Flight Ops. We get Greg Johnson, also known as Ray J's call sign, the Blue Origin vice president, and various other people. Sonny was there as well, of course, Sonny White. And so she's actually had some updates and some input into a talk today, which she's keeping secret, and I'm hoping to see what she's actually going to come up with that. She's also the events manager at Edinburgh Women in Space. Now, I know it's been rebranded, and I can't remember what it's now called. It's something that's now expanding into Scotland. And so they had a very successful conference earlier this year. And she's been working on a CANSAT project as well, which has qualified this year for the international round. So I think it's distilled from about 200 entries down to the top 20 or so in the world, which is kind of exciting, and that's sponsored by the American Association for the Advancement of Science. I've been given a couple of quotes about Amelia's dissertation, which I'm just going to read out to you. So from assessor number 1, about the thoroughness of the literature review. I have read PhD literature reviews with less depth. So I was delighted to hear that. And assessor number 2, this will clearly make a very good article for a journal. So I'm just going to stop there. Without further ado, I'd like to hand over to Amelia Stanton. Amelia.
Thank you. Okay, that is a lot of pressure to live up to in one introduction. But yeah, hi, I'm Amelia Stanton, Bob's daughter. I will just share my screen now. So today I will be talking to you about my dissertation research on the use of additive manufacturing for small payload liquid propellant rocket engines and then I was focusing specifically on combustion chambers. Just a warning, some of this research, well, I finished my dissertation in April, so I've been after talking to a few people earlier on this week, some of my research is a little out of date, so just a warning, but I have put up more up-to-date slides in as well. Okay, so today I will be discussing the objectives of my dissertation, and then I'll go into a bit of background research, so talking about combustion chambers and additive manufacturing for those who don't know about it. And then I'll talk about the case study that I focused on. I'll be looking at like the design, so I'll look at materials and manufacturing techniques. And then I did a finite element analysis and a topological optimization, and then I'll go through the conclusions and the next steps to my project. Okay, so the main goal of my dissertation was to look at additive manufacturing for combustion chambers to see if it can improve the design, the time it takes to manufacture projects. And I've seen a lot of people have been doing more research in additive manufacturing, but they've not been doing it in engine parts that are as big as combustion chambers. And I thought that's like the main reason I wanted to look into it, is because combustion chambers are quite complicated. They've got really complicated internal designs because of the cooling chamber. So then I looked at different current projects that have been going on that didn't really use additive manufacturing, and I found one by a couple of universities in Colombia called the SU-A11 rocket engine. And so my goal was to try and improve and reduce the weight, to improve, to lower the number of components used, and to reduce the costs. Okay, so additive manufacturing is the process of adding material in layers to form an object. So by doing this, it's like 3D printing, which I'm sure most of you have heard of. You print out layers individually, and this can allow you to make more complicated designs, freeform fabrication, so that it's also reduce costs because you don't need to worry about assembly processes afterwards. You don't need to individually manufacture with, say if you were using milling techniques or something, you'd have to mill it, then you'd have to go on to a different process to create your whole finished project. Then you also reduce waste materials, which also helps the cost, and reduction in parts needed for assembly, as I said. Okay, so in additive manufacturing, it's typically split into two types of systems. So bed systems and fed systems. Bed systems, are a process where you have the material lying in almost a bed formation. Almost imagine a mattress, and you've got the material, and it's normally either in a powder or a liquid form. And a laser is shone onto the bed, and it melts the powder or the form. So then as soon as it solidifies, as soon as it dries, it starts to form the shape, and it builds up like that. Whereas a fed system is where you've got, I'm trying to explain it in simplest terms. So imagine a water gun. So if you use a water gun, it's like that, but imagine it being like a piece of metal or a stream of material, and it's have a laser pointed onto it, so it melts it, and as it moves around the machine, it's able to form an object. So these are different types of processes used for each one of these additive manufacturing concepts. Ooh. Okay, so this is more recent research that's been done. So currently in June this year, Westcott, particularly Catapult, has invested in a metal FAB additive manufacturing systems. So this will be used for rocket propulsion products, like with drones and then other autonomous systems. So that's very exciting. And then relativity space. So I learned about them recently, and it was these two guys that came together. One of them was from Blue Origin and the other was from SpaceX, so very, very smart people. And they've decided that they want to be able to build a rocket engine, like the full rocket, completely from additive manufacturing. And they've started doing that, and they've come on leaps and bounds. They've just invested in a huge warehouse, and they're hopefully going to make a fully autonomous rocket development center, so they can build everything in a workshop, no people needed. And so by doing this, there's going to be fewer parts needed, like very fast production times, and you're not going to need any fixed tools. So combustion chambers. If you're not sure like what one really is, a combustion chamber is the part of the rocket where your oxidizer and your propellant mix together to form thrust, and then it goes right down through the nozzle, and that's what makes your rocket move, basically. So inside the combustion chamber, around the wall of the main combustion chamber, as you can see on this picture, there are longitudinal pipes, and that's a cooling system, because you don't want the outside of your rocket to be as hot as the inside of your rocket, because otherwise it's just not going to be very efficient. So it needs to be designed for extremely high temperatures, very high pressures, vibrational loads, like when you launch, acoustic loads, because we all know rockets are quite loud, and high speeds. So the case study I used was the SUA-11 engine. So this is from, as you can see, the ANKAA 6 rocket, which was another project that was done in Columbia Universities. The aim was to get it from sea level to orbit, well, not to orbit, to about an altitude of 14 kilometers. And as you can see here by some of the images, it did not work when they tested it. There was a bit of an error where the combustion chamber exploded because it got to too high a temperature, and the material and design could not stand that sort of force. Okay, so when I looked at my design, I looked at materials to start off with. So they used an SAE low carbon steel. Low carbon steel is really good because of the cost. It's really cheap, it's easy to manufacture with. However, if you look at it compared to a copper alloy, this copper alloy is actually invented by NASA. The difference in elastic modulus, tensile strength, Poisson's ratio, density, and thermal conductivity are quite different. I mean, the density for the copper alloy is a bit higher. However, since it's got higher elastic modulus and tensile strength, it will counteract. You don't need as much of it for the same amount of stability when you're designing. And then the thermal conductivity means it's better when for a combustion chamber because of the extremely high heats. So these are the designs. So on your left, you can see the original design that they came up with. They actually got to build it. Unfortunately, I didn't get to build it, even a prototype, because of COVID, but hopefully the aim will be to eventually be able to model it. So yeah, they use 6 different components when building it. They have like the nozzle that's separate, the combustion chamber, the cooling system, and then all the valves that are attached to it. They're all different components. So you have to go through a massive assembly process, whereas mine all made with one component, as you can see. Yeah, it's got all the main things, but less material is needed because you don't need to have bolts to like screw parts together because they're already built as one. I'll move on to the next slide. Okay, so in the original design, they used conventional lathes, they use milling, and they use welding. So each of those things need human input. They need to be done by a person or by CNC, but you can't CNC with welding, I don't think, or milling properly to the same level because they need to go through like a check process to make sure that everything is done to the highest standard. So with this costs more because, as you know, the most expensive part of manufacturing is the human time that it takes to do all these like verifications. Whereas with additive manufacturing, the only human input you need after the design process is to click the on machine on the additive manufacturing machine. So I chose to use direct energy deposition. This is done because it uses a fed machine, so you're able to do it in a larger space. You don't need to have like the restrictions or the size restrictions that you would for any bed system. It's been used on other combustion chamber designs, and it's been proven to work to a very high standard, especially for the inside and the outside, where you want it to be like a smooth, good finish. There we go. So as you can see, the original design, I did a finite element analysis and then I compared it to my modified new design. So the original design, as you can see, there is a little bit of a difference there. There's deformation clearly in the outside of the combustion chamber, and the red highlights how high the pressure is on the outside. Yeah, not very good, whereas mine is green. There is still a deformation, but this was later handled in the topological optimization. Ooh. Okay, so the stress analysis graphs show the stress against the number of elements, so how fine my mesh is when I did my finite element analysis. So basically a finite element analysis looks at the stress over the whole area of the combustion chamber, and then it I put the pressure on acting on the inside, the outside, all the pressures, the temperatures it's got to withstand, all of these different things, and then it will tell me how efficient my design is, where the high probability of fails are compared to like the material, so then I can improve my design through that rather than building something and then realizing it doesn't work. So then you've wasted time and money and you'd have to start all over again. So this does it for you. So the original design, as you can see, it's got a high of about 220 megapascals, which for those of you who don't know is quite high. Yeah, you don't want really any pressures that high within your combustion chamber that aren't like a productive force. If they're acting at the side of your combustion chamber, you're going to end up with like really bad distortion, as you will see in the next slide. However, if it's acting downwards, which is where you want it acting, that's all good, because the more pressure you have, the more thrust you're going to have. So then if you look at mine, I think the maximum one I had was 192 megapascals, so a lot less pressure in there, which is better. Yeah, so if you look at the original, they've got higher pressure. The displacement is a lot greater, so 3.6 centimeters instead of 1.32. So my displacement is almost negligible compared to theirs with the deformation factors. And then the pressure within, I was trying to keep like the same, because I use the same calculations and the same dimensions for both designs after using Tyskovsky's equations. And yeah. Okay, so then this shows the displacement between the two. I mean, mine does look a bit more jaggedy, I am aware. There were a few anomalies, but as you see, it curves down to a lower displacement. So mine is in millimeters and theirs is in centimeters. So imagine you've got a small combustion chamber and then you have like a few centimeters displacement. It's not good. Whereas you want like minimum displacement while the rocket is being launched, so then everything else will stay in place and you don't basically explode your rocket. And then finally, I did a topological optimization. So what this does is it looks at your design and it goes through the FEA and it sees where the points of failure are, and it looks at where you've got too much material, where there's no, like there is minimal stress there. So it looks at ways to reduce the material that you need to finish the design. So on the original design, this hasn't had any topological optimization, and you can see the magnitude in the displacement. So yeah, and originally it had a displacement of like 23 centimeters, which was ridiculous compared to the size it was. And I had one of a lot less. This looks at the inner size, but obviously, as you can see, minus times 10 to the minus 4 instead of times 10 to the minus 1. So it's, even though it's red and bright, it's not as high as the one to the left, the original design. So then this looks at the stress. It's like von Mises stress. As you can see, mine has no stress displacement on the external wall, whereas there is significant displacement on the external wall with the original design of like 1.83 times 10 to the 8, so 183.8 megapascals. My slides are unfortunately covering up. Okay, so yeah, 129.3, so a significant reduction in the pressure acting on the outside of the wall of the combustion chamber. Okay, so in conclusion, I was able to reduce my number of components from 6 to 1. The mass of the modified design did increase from 4.47 to 5.17. However, since the original design didn't work as it clearly exploded, like you needed the extra material. And then if you look at the manufacturing, the processes, the materials, mine would have turned out as a lighter weight compared to if they created theirs with the materials, the manufacturing, this, if it was like the same sort of process, mine would be weighing a lot less compared to theirs. And then the cost of manufacture. So even though the cost of my material was higher, the cost of the manufacturing processes and the material and all of the software that they used, it would have been more expensive to do their version than mine. And then they obviously didn't go through the same analytical techniques, so they had to build it, watch it explode, and then rebuild it. Whereas I can see where all my errors are, where everything has gone wrong, and so that will also reduce costs. Okay, so the next steps would be to perform CFD, so computer fluid dynamics, so I can see how the fuel interacts in the combustion chamber. I can make any improvements from that and perform thermal and vibrational finite element analysis on the internal and external walls of the combustion chamber and look at how the heat flows from the inside to the outside through the cooling chamber to see if there's any improvements that I can make in that. And then I will be manufacturing a prototype and perform testing in the workshop to make sure that everything is running smoothly before we start full-on development with like proper materials, proper costs, everything. So yeah, thank you very much for listening. I will take any questions if you have any.
Do you want to kill your presentation? Oh, thank you, Amelia. Thank you. Brilliant. Great presentation. That's it. Oops, am I muted still? No, good. And like me, you talk really quickly, especially when you're excited about something. So we've done it in almost record time. I think we only had one speaker faster than you. So I'm now ready to take some questions. Let me just pull up the chart. Now, so here's how it's going to work. I'm just going to switch to gallery view so I can see everybody. And I'm going to ask you to read your own questions if you want to. If not, I'll be happy to do so. You had there's a couple of messages actually in the chat. So Ange Mahorta said that you're doing a brilliant job of presenting and asked me to pass that on to you, which I've done. And Steve Salmon says, I may not be a rocket engineer or anything near, but this looks very impressive. I must admit, I was impressed as well. Nice work, Amelia. Right, let's have a look, see if we've got some. It's absolutely fascinating from Patrick Mayen. Richard Newland's fascinating. Right. So, questions. either try and track my attention here, or put something in the chat, and I'll try and take it in chronological order and let you ask your question.
Peter's got one.
Oops. Has it? Where's that? Oh, yes. Right. Okay. Peter Robinson, you've got a question. You're going to type it in for me.
It's already.
Oh, it's already there, is it? I apologise. Yeah.
How much of the improvement in the predicted stress displacement, etc., is due to the strong material, and how much of it is due to the design changes with the processes? So to answer that, I'm not sure how well you can hear me with this. Can you give me a thumbs up if you can hear me? Okay, cool. Yeah, you can tell we're in the same room since I'm muted. I did originally change the design, not the design, the material, and use the original design. And there was an improvement, but it wasn't as significant as I wanted, because then the weight was a lot higher because the density was higher, and other than that. But there was improvement for sure in the stress and displacement. I can email you directly and show you my original results with those values. I'm afraid I don't have them on this computer, but I will email you. Okay, so we've got I got some more comments coming in. How big was the combustion chamber? Yeah. Yes, I'll come on to it. Right. Right, so Royce Murphy saying she's not an engineer, but she comes from a family of engineers. She said it was very clear and convincing. Gosh, that's good. Delta V Media, that's Alan Marlowe, who's videoing today's event. Brilliant, really interesting, and really informative presentation. Richard Newlands asks, Richard, do you want to ask your question? Do you want to unmute yourself and ask your?
Since I work out how, yeah. Hang on, finger trouble. Sorry, I can't quite get the video working for some reason. It's been one of those days. Yeah, hi Amelia.
Hi.
I'm just wondering if you're intending building a prototype and actually test firing it on a test stand.
I am. Unfortunately, I didn't get to do any of that this year. I was spending a lot of time on call with my supervisor asking if I could go into the workshop to actually build something and use some of their additive manufacturing machines, but I wasn't allowed. But they said that if but they can hear me through yours.
Okay.
But they said that if I continue my research, I will be able to actually do a prototype and do an actual test on one of the fields near Heriot Walk campus.
Well, I think we can probably do slightly better than that up here in Scotland. But so are you intending actually continuing that research so that you can build a prototype?
I think I will be, but it won't be officially as part of the university. I think it would be on my own time, because it's just out of curiosity at this point.
Yeah, me too. I'd like to see that thing fire, actually. Yeah. Okay, thank you.
Next up, Alex Wood, you have a question about finite element analysis. Alex, do you want to unmute yourself and ask the question, or I'll read it? Okay. It keeps disappearing off my screen. Okay. Alex is asking, how computationally intensive is your finite element analysis, and how long does it take to run?
So that's the big words. So my finite element analysis, as you could have seen by my graphs, they went to a number of elements. So the number of elements is basically the number of little triangles that it splits your design up into. And so like the further you get, I'd say it was quite intensive. However, I was only limited to a student version of the software, so I couldn't do it as far as I probably could have if I had more like a further access to the software. In terms of how long did it take, the more elements that you're doing it for, the longer it takes. So I think my longest one was about 3 hours it took. So yeah, I went off, left it on my computer running made myself some dinner and then came back.
Okay, next up, Griffith Ingram. I'm just going to read it out if you don't mind. But you're saying, Amelia, have you considered writing this up as a paper for JBIS?
I have. After my comments, though, I'm not sure how good my writing techniques are. I got told that the standard of the detail is like PhD worthy, but I need to practice writing. So I'm not sure if it will be as well received.
So you need to practice, absolutely. Okay, Steve Salmon. Steve, do you want to ask your question about manufacturers?
Hi, Amelia. Brilliant presentation. Can you hear me?
Yes.
Yes.
Good, excellent, fine. Yeah, no, it was just to ask, really very similar to what Rick Newland asked, was that do you have facilities to be able to build the prototype? And if so, who is it who's going to do it, if that's not classified?
So I think after that I would have to talk to my supervisor to see if it'd be possible to build it at either university, and then if not, I would have to get private funding and try and do it that way, because I don't think I could afford it out of my own pocket.
So you said it was a Fed-based system. Do you have a Fed-based system at the university?
I'm not sure what facilities that we have at the university, but we do have Fed machines. I'm just not sure if they're the direct energy deposition that I would want to use.
Okay, great. Okay, someone called Stephen. Stephen, I'm not sure which Stephen it is. It's not Steve Salmon. I'm just going to read it out if you don't mind. Excellent, clear presentation. How did you determine the finite element analysis mesh density?
I'm trying to find where that question is. Okay. So I'm not quite sure what you mean by mesh density, but when I was doing it, I just created the triangles, and then I started just refining it to as small as I could possibly go. And it got to this stage where my computer wouldn't let me do it anymore. But yeah, that's just how I worked, and that's how we were told to do it at the university. I'm sorry if that doesn't answer your question.
No, it's okay. I mean, when you in FE analysis, you generally tend to use more elements to get the stress levels to converge. So to find the right number of elements to use to get a true representation. So I think you're limited by having a student license. So, yeah. But it looked okay.
Thank you.
Thank you.
Next up, we have a question from Anj Malhotra. Anj, do you want to unmute yourself and ask your question about 3D printing? Anj, okay, I'm going to read your question out, so you might be having trouble. Right, Anj's question is, how large are the actual 3D printing, the additive manufacturing machines to do this sort of building and manufacturing?
So a lot of them vary for their function. So obviously you can get the commercial 3D printing machines that you can probably buy and put in your workshop or in your office at home, and then they can range exponentially. I think the biggest one I've seen is nearly the size of a small warehouse, but it needs to be a clean room, and that is just for Fed systems. You can't use that for a bed system because of the limited proportion. But yeah, I think you can get some pretty big ones, but the bigger they are, the more they cost.
Next up, we have George Kersey. George, do you want to unmute yourself and ask your question?
Sure. First of all, can you hear me?
We can, yeah.
Cool. First things first, excellent presentation, Amelia. Very interesting. Secondly, did you consider looking at additive manufacturing of any of the other parts of the engine? So, for example, the nozzle?
Yes, I did. So with mine, it combines the nozzle and the combustion chamber, because normally they're two different components, but with mine, I thought it'd be easier to manufacture and assemble if it was just one big component. I also looked at injectors, as a few people know because I interviewed them when I was originally doing my research. So I think there is quite a lot of research done in injectors already, and that's why I wanted to look at combustion chambers, because there was a lot less research done in that area. So I thought I could make a few more differences and make a bigger splash in the water, if you will.
Great. And we're actually back to Stephen again. Stephen, you've got a question about NDT.
Yes, I was interested if you intended to carry out any NDT on the prototype.
Is that non-destructive testing? Is that what you mean?
Yes, yeah, non-destructive testing, sorry.
Sorry, could you repeat that question?
Do you intend to carry out any non-destructive testing of the prototype? Because AM tends to have occlusions within it unless you process the material.
The answer is yes, I would like to do that. I think there are different labs in my university that I would be allowed to do that. So I think the first testing that I would perform was literally heat and fluid dynamics testing, which we have a nice fluid lab in our university. And then I would move on to more looking at the stress and hopefully not breaking my prototype when I'm performing the stress needed. I remember in first year we did one of these projects and we had to build something, and I was really proud of what we built, and then they put it in the machine and the whole thing just snapped in half after undergoing quite a lot of pressure. I was so sad, but then I was like, no, this is good, like this means you have a lot to write about in your report. And I was just looking at my broken project and like, okay.
Okay.
Right,
Thank you.
I think next up we've got Patrick. Patrick's actually asked the same question we already answered with Neil, which was about the dimensions of the combustion chamber. He's asking how tall it was as well, or how tall it would. So for your product, how tall would it need to be? How big would it need to be?
So mine was about 250 millimeters tall, so 25 centimeters. So it is quite a small combustion chamber, but it was a small rocket. And then the width or the diameter was about 126 millimeters. So that's how big it roughly was. So 12.6 centimeters by about 250. I think people want me to unmute so they can see my face.
Yes, yeah, please don't. Yeah. Oh yeah, God, they're looking at me all the time. That's terrible.
Do you want me to?
Yeah, so if you unmute, it might still work. Oh no, I'll kill that. I'll kill my microphone. Right.
Okay.
Right. Okay. So next up we have Ed. Ed, you're into 3D printing with plastics, but you've got a question. Could you want to unmute yourself and ask?
How do I unmute? Where is it? It's on there.
We can't hear you, Ed.
You can hear me already.
Oh, it's because
It's actually Millie. I'm Ed's other half. And at school we do plastic 3D printing. It's quite different, obviously. And it's literally the very basic layer additive manufacturing. But I was wondering if you had to do anything to process this material to sort of homogenize the layers, or to homogenize the material in a way to make it strong enough to withstand the thrust pressures.
Do you want to unmute yourself?
Yes, I'll do so.
Please, sorry.
Yeah, thank you. So with the material that I chose, that one of the specific reasons I chose a copper, so I used CP something, was because you didn't have to do any like external like finishing products. So with additive manufacturing, you still might have to like mill it just to like make sure your edges are refined and everything. But with the one that I chose and the material I chose, you don't have as many like finishing or final products, or not products, but final processes that you have to do. But yeah, I think I need to do a bit more research to make sure that that is true, because otherwise I don't want something going completely wrong because I didn't top and tail it.
Okay, thank you very much.
Okay, next, Richard Newlands again. Oh, Richard, what are you saying? Aspire Space would be interested in helping you build and test Fire?
Yeah, we would actually. We're mucking about with liquids at the moment, slightly smaller than the one you're developing, but we are building. In fact, it's almost finished. A little thrust stand for student-sized type projects. So yeah, we'd be delighted to put something as august as a properly designed engine on the test stand, as opposed to something we've knocked up in a hurry and fingers crossed. So yeah, the offer's there if you'd like to test fire one of our facility. We'd be delighted.
Thank you so much.
Yep.
Oh, I can't stop smiling now.
Okay, next up, Ranji Gogoi. I hope I pronounced your name right. Ranji, do you want to ask your question? You want to unmute yourself?
Hi, all. I think mine was answered by it was a similar question to Millie, but I was just interested about the post-processing and if like powder removal would be an issue, or is it not worth the hassle cleaning it out?
So with mine, yeah, I was planning on not using a powder to make mine. It would have been liquid, so it would have gone through a fed as a steady stream, like almost like when you're soldering something. So it wouldn't have had to deal with like the powder removal and like just brushing everything off. I hope that answers your question. But yeah, I think once I said like I need to go through and make sure that there aren't any other final processes that I need to do to make sure that the standard of like the quality is enough to test it and not for it to like blow up or something.
Yeah, fantastic. I look forward to seeing the hardware.
Thank you.
I'm just going to read out the next one. The next one is again from Richard Newlands. He was saying he was chatting with Alan Bond, who said that of all the liquid engine types, LOX, liquid oxygen and liquid hydrogen, such as the RL10, would benefit most from additive manufacturing. And he's asking, how clean is the copper?
How clean?
Yeah, just with liquid oxygen in particular, if there's any contamination, it tends to go boom, catch fire. So I wondered if there were any residual, I don't know, chemicals in the copper once it's deposited.
I'm not sure. I haven't done as much research in that as I probably should have. But if I could maybe talk to you and you could enlighten me, that would be very useful.
Okay, no problem.
Okay. Next up, we've got Steve Salmon again. He's not sure if we've already answered this, but for the prototype, would you be using the NASA copper alloy or another copper alloy?
There is another copper alloy that's been developed by a British company. So hopefully I would get to work with them to produce it just because we're sport home team and like economically and environmentally we can like reduce cost of shipping it over.
Actually, I've got a question from Alan Marlowe. Alan, do you want to ask your question about cryogenic liquids?
I'm just wondering how these additive printing materials deal with cryogenic liquids. I'm thinking of liquid oxygen and liquid hydrogen.
So the research that I've done showed that it was able to work with liquids. I think it was like minus 50 degrees up until 800 degrees, that like that was its like comfortable range, and it was like minimal displacement or like reactions with the oxygen when testing. But yeah, I read a paper on it, but it was a few months ago, so I'll look over it and I might send it to you if that.
Yeah, I just wonder if I can be a bit cheeky and slip in another question. I believe the crew on ISS are using a 3D printer now.
Yes,
I'm just wondering what are the advantages and disadvantages of 3D printing in zero gravity?
I think it depends. So if you used like a bed system, that would definitely be an issue because you want everything to be lying flat when you print it. However, with a fed system, I think I'd have to do a bit more research, but I think that would be possible. But I know that the what they've been using up there has been really good because then you're able to create tools if they're broken or misplaced or anything. So you don't really have a limit. So once you're up there, if you run out of something, you can easily manufacture another one.
Okay, I'm going to call Patrick Mahon to ask his other question about lessons learned, things that you've learned from the project.
Brilliant, thanks. Brilliant talk, Amelia. Really, really interesting. But yeah, just wondered what, from your perspective, what was the most valuable thing you've learned from the whole project overall?
I think when I was researching what other companies are doing, it was very, very interesting. And then I was able to talk to a few companies, and that was really exciting, getting to talk to their manufacturing team and their engineers and seeing the really cool work that's been going on in this country. I think it just shows that Britain are definitely taking a huge step in the space industry, and it's exciting to see what we're coming up with.
Okay, we've got another question from Anne. She asked me to read it out. Do you know if there are any differences in the end quality of the products comparing additive manufacturing versus traditional manufacturing processes for these types of products, which will be under extreme stresses and pressures?
So yes, when initial research had been done with additive manufacturing, there was a difference between the quality of finish, because with additive manufacturing they didn't do as many final processes. So the finish of the quality was better with milling. However, it wasn't as economically viable, and yeah, there were other issues with the project. So there's obviously different pros and cons for each type of manufacturing. But I'll read over that question again. In terms of extreme stresses and pressures, there was the additive manufacturing process performed better because you didn't have the extreme stresses where the products were assembled. So for example, at bolts and with welding and stuff, that's normally the point of fail in these products. Whereas if you do it with additive manufacturing, you don't have those points of failure per se.
Okay, got a comment from Enrico Trulese. He said, sorry he needs to go, but congratulations for the work done. Additive manufacturing is the future of manufacturing, not only for spacecraft. I am sure you'll find a lot of interest from the industry. So next up, I think it's victorproduction.com. I think, if I'm right, you're a Serbian company in the space industry. Would you like to ask unmute yourself and ask your question to Amelia?
Yes, hi.
Hi.
So I was wondering, you engineered the whole engine and combustion chamber. So my question is, did you consider thermal stresses? And if I understood correctly, your fuel is actually cooling the engine. So why did you leave so much fuel liquids on the other side of the nozzle?
So with the engine that was designed by the Columbian universities, we use kerosene and oxygen. So both of those came from different fuel tanks, and then they were injected into the thing, and I think it was 10%. I need to look over the numbers, but the oxygen doesn't actually cool because they react, but there's about 10% of the oxygen from the oxygen tank, and that oxygen was used around the combustion chamber as the coolant, if that answers your question.
Yes, thank you.
And so the next question I've got is from Alex Wood. You mentioned British research on additive manufacturing. Is this something where Britain is taking a lead?
I am biased and I would love to say yes, but I know that there is a lot of work going on in America. So I think if we keep working together, we're going to create more advanced technology in additive manufacturing. But yeah, I think America is definitely making huge leaps and bounds in this, but Britain are too. So I couldn't say for sure, but I know that there are a lot of countries doing a lot more research in additive manufacturing, which I think is really exciting.
Right, there's a couple of messages now. Team Anderson is saying, thank you for a superb presentation. Sorry, I have to leave before the end of the Q&A. And Robin Brand as well, our own Robin Brand. I must go now, but well done, Amelia, and good luck in the future.
Thank you.
So are we happy? Have we any more questions, chats? Oh, Mark Perman.
Hi, Amelia. Thanks. Excellent presentation. Just some comments. The cleanliness of the internal galleries. You need to pay attention when you come to manufacture. You really do need to clean everything very carefully. Not only from the reaction point of view, if you put, as Rick said, liquid oxygen through and it picks, and you've got oil or other material in there, you'll have a nasty surprise. But also, if you've got any form of debris in there, and it can be quite small, by the time that's gone round the galleries and then into your injector head, if it goes into the injector head, then that can disturb your fuel oxidizer ratio quite markedly. And again, you can have quite unpleasant results. So you do really need to clean the chamber and the injector galleries. One I have, if it's any use to you, it was written in the late 50s, but it's called Design of Liquid Propellant Rocket Motors, and it's what the Ministry of Defence used to use. It's a very, very readable and very useful textbook. So if you wanted to borrow that, you're very welcome. Yeah, I think that was it for me. John Harlow, do you have any comments? I'd love to talk to you offline about your combustion chamber design, but it would probably be a bit detailed for this audience. So, John, do you have anything to say?
Yeah, thanks very much, Amelia. I'm if the system support group is still going at Westcott and I was heading it up, I'd employ you tomorrow. Yeah, fascinating. Yeah, there is so much going on all around the planet on additive layer manufacturing, and as you well know, Aerojet, for one, is very strong in that area. We do have some big, GKN, for instance, is very big in AM in the UK. So they don't publish an awful lot because they're a defence company and it doesn't go, it doesn't go into the civilian area, but they're pretty strong in it. I think all the comments that we had today are very, very relevant. And just like Mark, there's one or two books I could point you towards. You could borrow some. I'm a bit worried about the thermal stresses you might have at your nozzle throat, but we can discuss that offline. But well done and thanks very much.
Thank you so much. I would definitely like to take you both up on the books.
And I think starting to come to a close now. So Stanton made a comment. He just said, when you get to build and successfully prove your design prototype, hopefully with, following Mark and John's pointers, then please don't forget to copyright the design if possible.
I'll try.
Can I just say, I know people can't see, but you've actually got the initial sketch that you did just by your side. Can you show the remaining people there?
Yeah.
You should actually did start low tech before she used the CAD system.
I am also a bit of a child and coloured them in. But yeah, this is sort of how I designed them to make sure that they're like all one component rather than multiple. So this is how I drew them up on the FEA. Yeah, so definitely low tech, a bit childish, but yeah.
Richard says back of the envelope. Okay, so I think, is there any more questions before I end today's session? And George Kersey says low-tech approach can work very well. Absolutely. Yeah. In which case, I'm going to call an end today. So a big thank you to Amelia. It was a really good talk. Thoroughly enjoyed it. I think everyone else did as well. And we had, if you're interested, we had actually 100 register for today's talk, which is bang on the maximum that we could actually take. So the usual crew, so I'm going to ask the usual crew, I'd like you to, so if you're, so Steve Salmon, John Harlow, Mark, and anyone else that wants to just hang on, we're going to do a wash up in a few minutes. So everyone else, thank you so much for supporting us today. It's been really great to see you all, and I hope to see you again next month with Adam Hibbard's talk on the Ariane 4 guidance system. Just a few more questions, just a few more comments. You got a lot of thanks coming in now. You have to keep in frame that drawing, says Steve. Victor Production and Sylvia says thanks. Ed says incredibly interesting talk, Amelia. Thank you so much. Good luck in your future rocket engineering. And Adam says, who's doing next month's talk, says thank you, Amelia.
Thank you so much for everyone who came, and yeah, thanks for a first official talk. I think it went okay.
Well done. Yeah. Okay. Bye, everyone.
Bye.
Bye.